Yeah, welcome back to the second part of our practical lecture 11.1. Today, using data mining and recommender techniques in clouds. In the first part, we have actually used a couple of very, let's say, simple data mining techniques like a priori and FP growth in the Helmholtz Data Federation Cloud, which is an interesting open stack-based cloud because it's very different from Amazon. It's very different from MS Azure and Google Colab and so on, things you know. On the other hand, they share similarities, like having also, of course, Jupyter available. You have the possibility to install Python packages with pip. That is, I think, one of the takeaway messages of the first part. Take this as a tool. Remember this tool. Pip is incredibly useful. My PhD students can tell you a lot about it, using it a lot of times, including myself. Then basically in the end of the part, part one, we really thought about there are more aspects to data mining, similar like we use deep learning for the things that Charlie did with, having automatically tags in the database based on deep learning, basically. There could be also recommender systems. And of course, people have strong opinions sometimes and would say, well, recommender systems is not data mining, it's actually machine learning. Or others would say, lots of statistics is in this. So matrix factorization and so on, there's not really learning in itself. So when you come really to a practical setup in the market, my really experience is in the end, it doesn't matter anymore. You have a given problem, you have data at hand, and then you use a hell of a lot of statistics in the beginning to understand your data. We basically have a lot of ways of using data mining techniques, but sometimes we also have very fascinating tools like deep learning. So this is all in your tool set as a data scientist today. Just feel free to use it. And what we also will basically look into the second part now, which we start in the first part, is using this CRISP process for data mining. You see the CRISP process basically here in the middle, right? And the key thing is really to start with a problem understanding. So what is a problem? When someone says, hey, I have data, then you don't say, okay, what data, or what problem rather you want to solve. And we were saying in the first part of the lecture, this is collaborative filtering. So we want to give personalized recommendations. And these recommendations should basically recommend some item to a certain user that is not only bought by others, but is based on the interest of a very similar user B. And that's where the added value comes for, right? So it's not just any recommendation, it's one that most likely also is liked by me. What you also know, machine learning is never 100%. So of course, sometimes personalities, even if they are very similar, they have a very strong opinion on differences in one or two items, but statistics to the rescue would say that mostly in the majority of cases, the recommendation will work. So in the end, you would have basically rating matrices that someone would give you in the form of this kind of movie recommendation example that I want to play through. And that is also part of your assignment. So the assignment 3 is really just to understand it, because it's a little bit more elaborate. It's not just FP growth, a couple of lines of Python. Here is a bit more substance behind it, especially in the added value of learning so-called embeddings, which makes it the most difficult to understand, I think. So first of all, let's look at the problem understanding. So we have a matrix, and it's good to know that we have always two ways how such a matrix could be formed. It could be either explicit feedback, where that means usually that a particular user was liking a particular movie, right? And provides maybe a rating like +5. If you don't have that, as I said earlier, what you could do anytime is to think about 0 and 1s. So if he watched at all, he must have been interested. Otherwise, you don't waste your time usually. So mark it as 1, and of course, those that you didn't look, mark it as 0. So implicit feedback is this exactly, right? So that means that if a user watched the movie, I can give, this implicit feedback, at least he should have been interested. But in the majority of cases, the collaborative filtering engines work best or better with explicit feedback, because usually when the user is performing it, it has also certain variance, as I said, from the ratings from 1 till 5. or basically maybe even making comments and text comments about it. However, so the goal is clear, the business understanding is now clear. I want to have recommendations which are, similar to movies that basically some user has liked in the past. Of course, I want to have myself in it, so movies I like, but then of course I want to have in the future those movies recommended that fit to my history, but also that are similar to the users that are very similar to me. And of course, those that I don't seen yet, right? If I do a recommendation that I see a lot of times already, that doesn't make sense. Now, when we talk about this encoding, I think this is pretty clear. You can visualize this nicely, as you see here. Seen and unseen is a very trivial example. And to understand the embeddings that in the beginning we will form manually here, right? This is the idea of learning that automatically, but it goes some way until we get there. So that's why I have to here and there show you a little bit what essentially is there. And if you go now to the Google Colab that you have also in assignment 3, essentially here, lots of explanations are there for you to explore. So you can look here really in the Google Developer Zone and understand more, not only about collaborative filtering, also about content-based filtering. And to be honest with you, it's a very nice learning resource in general. So you would have lots of interesting courses. And the beauty of it is that you see also here, you can directly link it to a kind of Colab notebook which exists and which actually goes back to the learning exercises. We will see some of the learning exercises are then filled. Some are actually just black box solutions, but it doesn't matter. So once you do this and the problem understanding is clear, so to speak, you can maybe start this, but let me just reveal a little bit more about this embeddings. So the embeddings is an idea of have this latent hidden features that we don't really know. We want to learn them, but which explains then why some people are similar. And of course, you can now introduce a similarity measure. If you think about here on the left-hand side, this would be an example. You have children movies on the very one hand, right, liked by some. You see that personality likes these movies. Then you would have the other extreme of saying there's a really preference for adult movies. And of course, the movies I'm talking about, they're certainly different, and having another people set which actually looking them. Certainly there is a gray zone in terms of, a lady here in the middle maybe look Harry Potter, but also still something on the adult side. On the other hand, some people maybe also have fun with Shrek, but still also look Harry Potter. So this is not an extreme, and that's why we need the kind of actually numerical values here helping us in this latent features. And what you see here is actually now manual crafted features on the one here, which is represented the preference for children and adult movies. And then basically the other one that you have here, sorry, for the preference from the people here having actually this children or adult movies. And then of course you have the other tendency, if they are looked by children's or adults or for children's and adults, as you see here, The Dark Knight Rises, Batman and so on is rather an adult movie, Shrek often more for children. So by having this movie embeddings and user embeddings, right? So this is a user embedding here, and this is a movie embedding, admittedly very trivial, 1D. We will see how that normally is then done with 30D or 35 dimensions, or if you have larger data sets, even more. But what you also see is there will be some cases where this is extremely trivial, right? So I was alluding to this one, for instance, where it's very clear. And the user watched these basically, and this can be very well explained, right? Because these are adult movies, these are kind of more children movies with a medium part in it. And if you now multiply, and this is the idea of using dot products here, essentially, if you multiply and having a value which is most likely closer to 1, then it's very likely that the user actually is looking at. And think about that this latent features needs to be learned because nobody tells you about this. So the values that are here needs to be learned. And the beauty is we have already this. We have this rating matrix here given, right? So this is our constant in learning, so to speak, and we can adjust this latent features in order to basically come closer and closer to the solution that has this rating matrix here. Now, when you go deeper into this, you can imagine 1D might be not enough. It's not enough to really express the difficult cases. It's not deep enough to learn really. And particularly you see that in these two, let's say medium people that are watching, movies from both sides. So it's not really well explained yet. So especially with those numbers. So we have to go 2D, and nobody is saying that's a problem. So you can introduce another feature by manual hand, what we do now. And we could say, for instance, is it rather a very art house game, art house movie with these bows, or is it really a blockbuster hitting the cinemas with Batman and so forth, or Harry Potter, of course. So another manual feature we ingested, and from this you have an encoding. You can, for each movie, assign this and basically then learn from this, these kind of 2D features, which is now a 2D user embedded and basically a 2D movie embedding. So this embedding space, so to speak, is an abstract representation, which is now for the movies, for the users. And in a way, what this helps us is now to identify the similarity. And the beauty in this is now really that this can be automatically learned. What I did here was doing two manual features, and very similar. Essentially, the Google Colab notebook will take you through this and will explain it to you in these ways. But this is just, let's say, the basics to understand it, that you can learn these embeddings actually fully automatically. You don't have to say it's a blockbuster or for adult. All what you need to have, and this is of course the only requirement, is this kind of rating matrix. And of course, this is always what I said earlier, the data you need to have, otherwise you can forget to do data mining, of course. But if you have the rating matrix, you can apply basically this collaborative filtering. Now, as I said, it's a little bit more elaborate, thinking about different ways how we can optimize this and learn from this. We had in several lectures already that we talk about learning in the terms of optimizing. So in a way, you would have here the encoding of the rating matrix as, of course, values here, but this is given. And what we need is really this here, these embedded features that we learn. And the idea is to have there two matrices really, which is n times, which is a number of movies here towards the dimension. So here 2, but could be 30, could be 35. And it depends only how much computing capacity you have in a way, right? So you could make it deeper and deeper. Then, of course, you have a matrix U, which captures then all the user ratings or the user embedded weather, which are M users, also dimension of, D. So, and by doing this dot product, the learning goal is really to have this rating matrix A, which essentially is an M cross N matrix, to be really, approximated as good as possible. That might be not 100%, it's machine learning in a way, or data mining with having optimization, but still we want to get really close with it. And by having more and more dimensions in the embedded features, you can actually achieve that. However, sometimes, of course, it depends now what data do you have. So sometimes you have trouble with saying if you have a very, very sparse matrix, right? As I said, in the movie database, chances are that you're not like these people covering most of all everything. In a normal production setup like Netflix or Amazon Prime, you have an extremely sparse matrix and you have just seen a couple of things. So some of the methods will not really work in that case, while others can be just better used for this. So in this example that we take here, we have several options. We take here the weighted matrix factorization approach, which on top actually is using then the SGD that you already know from lecture 6 and lecture 7. So stochastic gradient descent level. And here, of course, we have a 2D setup here in this play example, but that's what we want to essentially then we'll explore later in much more elaborate detail when we go to the Google Colab. The interesting thing is we introduce a hyperparameter, and this is also learning experience when I take you through this Google Colab here in the second part of the lecture, because this is of course loaded, the hyperparameters, like you have learned in deep learning. It's nothing else. The hyperparameters are your configuration options, are your difficulty. You don't know exactly how to choose them in a very systematic fashion. So you have to already, of course, sometimes explore with this. Now, the business understanding is now very clear. Let's get to practice a little bit when we now go and look a little bit through this notebook. The first things you do, however, when you start this up, you will see this on this example here that you are in the Google Colab zone. My recommendation is always save copy in Drive first. So then you basically have that in your own Google Drive, as you know from one of the previous lectures. There's no difference from the CNN, so I can always go now, and you see a little bit here symbol here, it's stored in the drive here on the top, right? So marking it's now in the drive, or I can click here and then I see, of course, firstly, the Google Colab environment here with my different neural network models that you know already, but also the kind of Morris recommendation systems Colab that you know basically will tackle here today. My recommendation furthermore is to really rename it. You can always here on top rename it, and of course you can stop working on it. Like for instance, if you want to have connect or not and look on the manage sections, that's what we had, so nothing is there. You can just close that maybe, and every time can come back to your old stored ones in the OneDrive, and then you just have to basically pick the connected app, which is a Google Collaboratory, to come back to your environment. Essentially, that's also here on the slide. So save the copy in Drive, rename it, save it, and I think that's pretty clear how to do it. You see a very nice preparation that you just have to work through to a little bit understand it. The idea of the assignment this time is not so much of making 100 million screenshots for me, but to really understand a little bit for the assignment what's coming up. You see a lot of yellow boxes you have to learn for the exam. And I think the assignment is a very good way to learn about this and to really understand it, because otherwise you would just go through the walkthrough and hit enter, 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 and have basically no learning effect. But here are different learning effects in it. I augmented it a bit with a crisp DM perspective, which is one of it, but then also the sensitivity for the hyperparameters, which is another one. Right, so you see essentially every time I do now something on the Google Colab engine here, you have this also very nicely in yellow blocks described what to do. And of course we start here a little bit now with the practice, but I will go back and forth. You find nice information behind the data set we're going to use, Movie Lens, for instance, which is a very known data set in two forms, really. There's a research one, which is larger, and also for educational that we use here. And although you can use here this data set also with neural networks, and it's part of this, you don't have to do this in the assignment. Right, so the assignment stops essentially with what I'm presenting here, just inspecting the embeddings, learn a little bit about regularization, that's important as you remember, and then basically get started. But before you start, you know the game. I hope. Connect to the hosted runtime is your first idea, so that you basically have now the access to the cloud there. You know where you're running, you have lots of memory usually, and lots of space. You can maybe check what is your runtime type. A GPU is here now very important because I want to make a specific case in one of the lectures for it. If you stay too long in the GPU and it's not used, they will warn you and will say, please go to the normal system. So we start here with a very interesting normal way how to use Jupyter notebooks. Essentially now in the Google Colab, there's no special things to point out. There are lots of different imports, as I can imagine from the beginning. Many things the pandas working with data frames, scikit-learn, TensorFlow. What I said is interesting because we don't use it for neural networks here. We just using for manipulate tensors. Then a couple of things for better display of the Panda data frames, which is more configuration options. However, interesting is the installation here of Altair. We know Matplotlib is very much known for visualization and graphics, and Altair adds a very nice interactivity to it, and I will show it later on. Then a couple of ideas that you can also contribute with user ratings in a spreadsheet, and this would be then integrated. Although we executed this here and you see in the outcome it was successfully installed, actually using indirectly similar commands you already know with pip install, right? So you see you can use pip install also out of Python here. But the point is also thinking about that you have an environment which is now very flexible, so you can play around. But here the idea of Google Spreadsheets to finalize this is really that you move shortly to another space in Google, can nicely authenticate with it, having an OAuth client, and then actually reuse these ratings that you just enter in. This is optional in your assignment. You can do this. I leave that out. So I think this is not, let's see, the key idea or learning experience that you can do when you add new ratings. Of course, if you do it a couple of times, then it could maybe influence a couple of things, but it's not what you have to do in the assignments. Now, the second part is really using this movie lens database. And again, the slide set will give you some more information about it. You imagine from our outline of how to do data science, we have always some training examples. And what that could be, of course, it's the ratings, it's the movie information, it's the user information, it's all the information we require. And with this, we're already starting the second CRISP DM process that you see here. When we come again to the CRISP DM model, we're now in the data understanding phase. So we're downloading the data. We don't really prepare it yet. We just look what's actually here. And you see what we're using is a 1000K. So it has so many ratings, 100,000 ratings. Okay, that's something. You have a lot of spreadsheet time to actually do this. Then there are lots of movies and 600 users. So it seems like a reasonable data set. If you want to do really basically a more research-oriented one, you have here on top one, which is the 25 million data set here with 160,000 users, right? So there's much more data. And you're also, let's say, invited to try that out. You can just simply actually change this line here and move it to the other that is provided here as a zip file. And with this, it just, will work, but of course will require more memory, will require more time to run, as you can imagine. Right, so by doing now this data understanding, the first idea is what data do I have? And you see we have here the user ID information, of course. We have ratings from these users to certain movies, which is important, and also when they did this. We have the genre, which is very interesting for us later to analyze the data. And of course, then also information about the movies. And that's how you start in the CRISP DM process. However, you also notice we have to start very quickly then when we want to understand the data, maybe visualize the data or doing statistics with it, we already move a little bit to data preparation. So we want to see and prepare some data structures here, for instance, shifting them for better displaying, or do certain other things which are not so important right now. But to prepare the data for several other aspects is of course something what you know already from the MNIST dataset as well. So for the data understanding, then jumping back, you would have essentially here this downloading that you just have to do. So I go back here inside this. We have actually installed it. So now you see you just execute the next with the things I just explained on the slide set. And what's happening now is that we want to explore a little bit what's happening here. So users describe. Here we have already some simple features from essentially lots of different statistics I can do. The more you go into this, you have, for instance, a count of how many user IDs there are. You see 943, for instance, are unique, and that's better be the case because otherwise you would have duplicate users if it doesn't match, or little less users. Then you have other ideas of how many different occupations are there, what is the most occupation, and so forth. So that's how you start having different statistics. I think that helps you better to understand the data, and is of course also here explained again in the aspect here. But another point I wanted to make, of course, here is really then thinking already what is actually here in the lower part, that we have a train and test set, right? So again, also when it's not deep learning, also when it's not logistic regression, now also with the movie recommendation, we have the same idea, put away, the test set for later to come back and do everything you do on the training set. Secondly, what you will see if you use a notebook, don't be scared if this is coming. The minute you take a coffee and run away and you have a GPU token as a runtime, then of course you can imagine that Google doesn't like it, that it's unused. It's very precious, this resource. So it wants you to change to the standard runtime without accelerators. So sometimes you're automatically also logged out. So this could be errors, which are frequently asked questions. So just remember this. So having this basic statistics, let's go into some visualization. I talked to you about the Altair visualization library. I can really recommend this. It's amazing what you can do with it. And I best explained when we go a little bit back to the notebook here. We do now the Altair here. And then have essentially user ratings here. So here you see essentially a couple of statistics as well. But the nice thing is it's interactive. It's related to each other. So you can click on some things like, different jobs people have. And then you see students. You see this is already an indicator for our data set. So this is a bit problematic that the count of records, which really students have, rated, is by far orders than many others here. So it's already something what you in the data understanding phase have to put in your brain. And of course you can now think about, okay, they seem to rate quite a lot here in the medium space, while others may be much more optimistic in the 5 space. So, I mean, this is just basically looking through the data, have data understanding along the way. And the nice thing really is with this notebook from Altair included with the visualization, you can do not only saving it and so on, but also interactively using it. Once you do it for users, what you want to understand is the mean user rating, maybe how many ratings per user. It's also interesting. You can do the same to movies, of course. That's what we also are interested in. So let's do that for the movies. Let's see some simple statistics for this, which is again using essentially lots of different ways how to count. You can see Star Wars apparently was often rated, and you just take the head of the 10 first. You can, of course, vary this with 20 or so. You see the rating mean. So it's generally we would say Star Wars is quite good rated as an example. Then you can go further and think about basically different parts of the lists and so on. And this is, I think, a bit self-explanatory. You can see how many ratings on what times of the list. You can navigate through this by having maybe some other rating count here justified. But nicely are also this visualization again, which again is a very important part. I also noted this here in the different slides for you to download. Firstly, remember we have a slightly student bias here, right? We see much more students have rated here than any other. Probably a professor put it out for students as an assignment to rate those movies. I don't know. But the point is this has implications on your data. And that's why the data understanding phase is often supported by data visualization, really showing this. And it's part of the data understanding phase. Equally for the movies, we have now seen 2 troubles. And essentially this reflects to the point that apparently the count of records or ratings for movies in the drama category is by orders of magnitudes more than all others, like Western, for example, right? Or comedy. There is much more happening with this. So whatever we do, we have already in the data essentially a bias towards this. Right? When you do recommendations now, you would assume there's more likely that dramas will be recommended or comedies because the signal is stronger. I have much more cases on this. There are elements how we can tackle this, like regularization, we will come to basically later in the lecture. But this is an important part of the data understanding to understand if I have a class imbalance in a sense here, or I have other properties in the, let's say, statistics, which are, making the data a little bit a problem. And either I can sample out, there's possibilities around that, or I do smart regularization strategies and so on, which I come later to. So by done this, we have seen we can gather information about users, we can gather information about the movies, and now it comes to the next part here in the Google Collaboratory when you move through it. And here, just a couple of snapshots are okay to do with your name here in the notebook, of course. But essentially, it's for you to learn the material and to understand it really. I think it's a very good example to understand collaborative filtering perfectly. One of the points why we use TensorFlow is exactly this one. If you remember what we said a little bit the last time here on having this user embedding, which is, of course, here in this play scenario, just 2 dimensions, but could be, let's say, in a real scenario out there 30 or 35 deep in terms of dimension. The key trouble we had in this movie rental example is, of course, the sparse metrics. And when you now save that in, let's say, 60,000 movies to the one end, and let's say the other one we said, I think we're 600 users or so on the other hand, then you have a very, very huge matrix, which is mostly empty, right? Here's it very good as an example, I think, explained, because people that look movies, I mean, basically rated a couple of them and not all of them, which means if you have a full rating matrix, here just as an example with 4 movies, still the most of them will be 0, 0, 0, 0. And just a couple of them, let's say, will be filled. So the TensorFlow software tool that you already know is actually good for deep learning. That's what we already know, doing backpropagation and so forth, but can be also good and nicely used for tensor operations, which is a key ingredient of deep learning, but also here in the matrix factorization. So here we're talking about already moving from the data understanding to the data preparation. And with this, a little bit to the modeling, because we want to know, think about how does our model look like. So we talk about a dot product structure with U and V that approximate A as a rating matrix that I already have. So I also have to think about what data structures lead me to this. And of course here the A should be a matrix. This is a one consideration, and then the dot products we learned as well as another. So now it continues a little bit talking about, so basically I switch back here to the collaboratory that you also see it really works. You start a little bit with this creation of this sparse tensor representation. You see complete this section. It's a little bit an exercise scenario, but the solution is directly given. So also here, the idea of the assignment 3 is not that you fill in this by your own, rather walk through as I discussed. Otherwise, it would be a quite big assignment at the end. That's not what we want to do. Rather, we want to use it to understand what collaborative filtering is. Now, when you were at machine learning, one thing was the data. The other one was how we learn. You remember in one of our diagrams, we put the error measure, right? And as we have A given, the ratings matrix, we always can compare to A for certain entries. And we said, basically, we want to have a product of U and V. It's here with a transpose notation saying essentially, again, the same, the dot product between both. So in this sense, you have here a definition of a mean square error that you can apply, and of the observed entries only. And this is a problem we will see later because of drama, which has lots of observed entries, and other areas. So we have a bias already in. And we see that essentially the recommendations might be into trouble. But for the beginning, the squared error here is often, and the mean squared error is actually often used in machine learning as a major error. And this is what you define essentially in the next lines here. So also there's not much to talk about. Again, it's setup here of solutions. Don't worry about this. The nice thing in this Jupyter Notebooks or Google Colabs is essentially then this, that you have explaining text along the way, which makes it, of course, very beautiful to learn more. You see a little bit the problem and why you need an alternate solution here in the mean square error, essentially saying that you otherwise would have all the observed pairs. And what you can do is to have maybe this, sparse tensor in a way arranged that that the memory costs you have for the part are looking really more on the embeddings only. And the embeddings, of course, have a certain dimension and are not directly n times users and times m, movies. So this is, of course, a different perspective. And exercise 3 is now exactly what I omit. So I think also for you, you don't need to do this. So this means, as I said earlier, put your own user ratings in. It's maybe fun, you can do this, but you can also leave it out. to really also stick with the time here in the class. I have to leave it out, but essentially you can try it out if you like. Now, much more, continue maybe a little bit also with the slides so that you see you have, of course, everything also on the slides. We discussed a little bit the mean square error. I think it's very trivial. You can imagine that this is a very straightforward notion of error. We are in the modeling phase of defining the error measure, because usually always the error or identifying and measuring alongside the error in training is, of course, part still of the modeling. Evaluation comes later. We have an embedding dimension to think about. This is important. And as you see, the first hyperparameters and really training here of the modeling will start with this next part of the script, where we do a collaborative filtering model with several embeddings. We can justify a learning rate, which is about your gradient descent optimizer that you already know, right? To minimize this error function we just defined with the mean square error. And there's lots of text where you don't need to know that by heart. I think several things are important, like here the SGD, for instance. And then what it does really is learning these kind of embeddings. Of course, not just two. It depends on how many you put in. And here we see how many number of iterations you train, another hyperparameter. And it looks good. So basically, when you train this, you execute this in the Jupyter Python notebook here today. We can do this, create this model. And then we build this model. It actually reuses, of course, parts which we have here defined as the collaborative filtering model, and essentially returns in this model something about this loss function that we defined, the embeddings we defined, and the metrics. You should do that your own, but again, here's a solution which is a little bit hidden. And we doesn't bother, because we're most interested in this here, which is now basically building and training the model and what's coming out of it. You see more hyperparameters, the embedding dimension of 30, the standard deviation, the learning rate, things which already mean something to you, the number of iteration, and all looks good if you also come back to the slide. So we have a low training error and actually following suit with a test error. So this seems to be all right. But you have to check, right? Now we're coming more into the sphere of evaluation. So, and evaluation could be on very different terms. You can see, are the movie recommendations good? There's a technique called nearest neighbors of some movies. They should be in the embedding space very close to each other. Norms of the movie embeddings could matter there. Visualization, they have lots of different opportunities to do so. Here are scores of candidates using the dot product of cosine, dot product and the cosine, which is essentially two measures we use here. In the Jupyter notebook, this is nicely already implemented, so you can just go ahead and use a solution there. No need to program that your own. And the details, again, would fill each university lecture. So in this sense, don't go in all the necessary details, but it's still a fine, nice book to really play around if you like. And when we do so, we have some user recommendations here we really want to see now and go through the modeling, which is basically here then calling the function we defined above. And when we have the movie Aladdin, we maybe want to know a little bit about it using these two different scores here, and measures really. You see we have Aladdin, but suddenly Sound of Music. So that's strange. You also observe drama and drama and drama and drama. And you realize from the beginning there were lots of drama. So in the data set, hence it seems like our model is a little bit biased. And we can prove that a little bit by looking on the embedding norms, which you also should go a little bit more in. You then do the assignment. We do it in parallel here now in the Jupyter notebook, the embedding visualization code we do here, which is again using a little bit the idea of to see how the norm really looks like from the number of ratings. Here we see in the other side. Then the solution to really think about that we maybe play around a little bit with the initial input or the initialization, right, of these models. We didn't discuss it. It was a really cold start. And you see here when you do a model, which is already certainly, let's say, a little bit more initialized properly, using basically some statistics. It's running already quite well. Of course, it's still the same curve. You would say the train error is going lower and lower and soon starts overfitting. If we don't stop here, maybe because the test error you see is perhaps going slightly up again, that's the reason for stopping, right? So we seriously overfitting here. And essentially, this is all also in the slides, and of course, your idea of using the assignment, right? Think about that we have from the evaluation some problem here with our comedy and drama. And you can always use the slides here in parallel to really identify this and to really talk about this and understanding this. There's a interesting way of having this high dimensional feature. You notice we use 30 dimensions of embeddings. This is not visualizable, but with TSNE, stochastic neighbor embedding, there's a chance of doing so. And with this interactive aspect, we could go a little bit through this and see for horror movies or children movies, which would be quite different, the clusters are not existing. So there, you would assume if this is a latent space, there should be formed at least a couple of clusters or something, but it seems to be all over the place, especially the drama. There is something wrong in our model. And this is actually what you can find out here. There are certain regularizations now which we'll apply. And regularization, as you remember, was now penalizing a little bit the modeling in the learning process. So we put essentially the regularization here below, close to the loss function that we defined before. And then with this, we also have this new hyperparameters, really, this regularization parameters. One is a gravity term and the other one is a typical L2 regularization that you have to define on your own. But regularization helps to keep these imbalances and a couple of others known also as folding basically under control. And one of the ideas why folding is also happening and the model was so poor is that we used actually just observed parts of the rating matrix. What is with those which we never basically have seen yet, which are the zeros, right? The unobserved parts. So this is now also the solution changing to the amount of data that we put in to thinking about that the unobserved things still matter. It also tells you something. But in a way, this is just one path through many options. You would now start off as a practical machine learner to go back to the modeling and say the evaluation was poor. So what to do? We have regularization. We could play around with the hyperparameters for the regularization here. We have a better embedding dimension maybe. We start with a better initialization. Maybe that will help. We actually train longer, although we see maybe that's okay because the test error still not goes up. So we can maybe train longer, but immediately if it goes up, careful if you remember, even if training error is 0, that means the test error is what's important. And then, of course, using different optimizers, SGD or so, would be another option. In a way, the same applies like we had in neural networks. The hyperparameter tuning is tough. Now, when you do now back to the model evaluation, we can do the same things with the norms. And you see now the difference between essentially the norm here in part of this, where you say that is a normal model that we had. And then basically the regularized model, which is interestingly much more in this direction where it matters. And when we think about improving, there's less drama here. That sounds appropriately. So let's go a little bit back to follow suit in the practical assignment here. We have a regularization model. Sorry, I didn't execute the solution yet. So we have a regularization model. We can look. You see it's trained here as we did with our neural networks, knocking the error down, a nice graph. But now we want to have, of course, also our Aladdin checked, what's actually with it. And we see already there's less drama in the game. And this is, of course, here the norm comparison between the normal model we had before. That's how you can also in papers or reports show that you improved the model. Again, we want to visualize the model maybe before we come to the end here today. And we want to improve it, and that means it should show some clusters. We have an embedding space here, an embedding, let's say, space, which is, of course, reduced using the TSNE technique. But when we now use horror, for instance, we should see clear clusters, right? Much clearer as before. Or children should have clusters which are not the same, but very much different. And you see, actually now, compared to the previous versions we're forming some forms of clusters here. You can continue now using softmax, using neural networks, but I think that would be too far for the assignment, also for our lecture, which is already at the end. We have done the evaluation. We have been going through the whole process of CRISP. With this example, we come to a situation where we'll think the model is already okay to be deployed. We could always improve it with using, for instance, different optimization algorithms. Maybe alternating these squares is often also used in practice. I used SGD because that's what you already know from previous lectures. And you are at the end of the CRISP process, and much more you don't need to really have in the assignment. Important is that you realize what's written here, because I will come in the assignment, in the exam, back to some of these questions which are in the yellow boxes. So just a couple of screenshots would be important to do when you do your assignments, that you really executed it. Make sure you see your name in the Google Colab. And that's all for the practical lecture 11.1 today.